Let's talk about highest common factors. So this is a topic from 300 BC. Euclid has a very interesting way of figuring out highest common factors. But before we go into that, let's first understand what highest common factors are. So what is the HCF of 12 and 30? So to figure out by definition what is the meaning of HCF? HCF is highest common factor. So what are the factors of 12 and what are the factors of 30, and then we have to find out the highest common factor of 12 and 30. So first let's think about what are the factors of 12. We have these possibilities 1 to 12. So let's check one by one. 1 is a factor of 12 or not? Yes, 1 divides 12, so 1 is a factor of 12. Let's move on to 2. 2 is a factor of 12 also because it divides 12. 3 is a factor of 12 also. Similarly, 4 times 3 is 12, so 4 is a factor of 12 also. 5 is not a factor of 12 because in the table of 5, in the multiplication table of 5, there is no 12. So 5 into 2 is 10, 5 into 3 is 15. There is no 12 in the multiples of 5. So 5 does not divide 12. That's why 5 is not a factor of 12. Then let's go to 6. 6 is a factor of 12. Yes, 6 into 2 is 12. 7 is not a factor of 12. 8 is not a factor of 12. You might feel that this is taking very long. We haven't even figured out the factors of 12 yet. We have to figure out the factors of 30 also, and then figure out the highest common factor. This could take a long time, but let's first do it the longer way for the sake of understanding of the meaning of HCF. 9 does not divide 12, so it's not there in the list. 10 does not divide 12, so it's not in the list. 12 or 11 does not divide 12, so it's not in the list. And 12, yes, it's in the list. Okay, a faster way would have been, like, if you're thinking about one, then think about 12 at the same time, right? Two numbers at the same time. You find two factors at the same time. 1 and 12 are factors of 12. Then you go to 2, and then you see that 2 into 6 is 12. That's why you can't have 7, 8, 9, 10, and 11. So remove them. Okay, this is faster. Then you come to 3, and 3 times 4 is 12. So you can't have 5 also. And then you very easily get all the factors of 12. Then using the same idea, let's figure out the factors of 30. 1 and 30, 2 and 15, 3 and 10, 4, no, 4 is not a factor of 30, 5, yes, 5 and 6, and that's it, because 5 and 6 you can't have more than that, because after 5 you have 6, but you have already had 6 from the descending part. So these are all the factors of 30. Let's check the common factors. 1 and 1 are the common factors. 1 is a common factor, and then 2 is a common factor also, but we need the highest common factor. 3 is a common factor also. 4 is not a factor. 6 and 6 is the highest common factor. Okay, so now let's see some other examples. What is the HCF of 1080 and 30? So what we did before is just for the sake of understanding of the meaning of HCF, because if you try to use that way to find out HCF of big numbers, and it's like if one of the number is big, then you will have many factors and it will take a long time to figure out all the factors. So you don't have to write down all factors and figure out the HCF. You can just check if this number divides this or not. If this number divides this, if 30 divides 1080, so 30 is a factor of 1080, and 30 is a factor of itself also, and 30 cannot have a factor greater than 30. That's why the HCF is 30, right? If you follow that logic, then you know that you don't have to write all these factors here and then factors of 30 and then figure out that the highest common factor is 30. That will take a long time. You can just understand that if you're checking the highest common factor of two numbers, one of the smaller number could be the HCF, or the HCF could even be smaller than that. But first check for the smaller number. Out of the two numbers, you check 30, if 30 is the HCF or not, just by dividing it to the other number. So the highest common factor of 30 is 30, and the same thing which I explained before, the reasoning here, the highest common factor of 30 is 30, and it's also a factor of 1080, sorry for that, 1080. So the HCF should be 30, right? So in general, like suppose A is less than B, and HCF of AB will be A if A divides B, right? The smaller number will be the HCF if it divides the bigger number, as simple as that. But let's now take some another example. Like what if you have to find out the HCF of 1080 and 1079? This is also a very simple example. If you go on and figure out the factors and then decide the highest common factor, it will take quite a long time. So the factors, there's no need to write down all the factors, because you can see something which is much simpler than that. If you write down the factors of 1080, you will have so many factors, and 1079 you will have so many factors, and guess what, the highest common factor is 1. Why so? Because any number greater than 1 which divides 1079 is bound to leave a remainder 1 with 1080, right? You must have seen, like, let's say 2 divides 6, right, 3 times. Then you have the next number of 6, 7, and you divide it by 2, you get a remainder 1, isn't it? Let's see one more example. Let's say 3 divides 21. Then if you have 22, you know that because this number is just 1 greater than 21, so now you will have one remainder for sure, right? This remainder is 1. So similarly, if any number divides 1079, let's say 1079, and you have an x here and it divides it completely, there is no remainder. You have a y quotient and there is no remainder. But if you use the same number to divide 1080, you are bound to have a remainder 1, isn't it? So if you see that, and x would be any number greater than 1, because if you use 1, then it will divide all the numbers. So for any number greater than 1 which divides 1079, which is a factor of 1079, is not a factor of 1080, because it will not divide 1080 completely. So any number greater than 1 can't be the HCF. That's why the HCF should be 1. So writing down the factors and from there figuring out the highest common factor is not what you would do when the time is when you have less time, right? So Euclid saw all this and he figured out a very easy way to figure out HCF, in which you wouldn't have to write down all the factors. And what was his algorithm, which is called Euclid's division algorithm? His algorithm is a recursive algorithm. You will have to follow some steps again and again. So maybe you can succeed in just one step, but if you don't succeed, you might have to follow the step again and again. So for two numbers a and b, b is smaller than a, and you have to figure out the HCF. He says the first thing is, of course, you check if the smaller number b divides a or not, if a is divisible by b or not. If yes, then the HCF is b. Talked about it. And if no, then the HCF is, this is the key step. This is something which is important. If no, then the HCF would be B, the smaller number, and the remainder which was there when we divided B by A, because B couldn't divide A completely. There must have been a remainder, and that remainder is written as A mod B. No? So A mod B means when you divide A by B, when you divide A by B, the remainder which you get is called A mod B. For example, 5 mod 2 will be 1, because if you divide 2, if you do 5 by 2 kind of division, divide 5 by 2, then you have 1 remainder. Okay, similarly, if you have 25 mod 13, then if you divide 25 by 13, you will have a remainder. How much? Oh, 12. That's a big remainder. So this is just a symbol to write down the remainder simply. A mod B is the remainder when A is divided by B. And what he says, like if you were unsuccessful in the first attempt, if you tried to divide B by A and it wasn't divisible, then the second step is like you can figure out now that the HCF would be the smaller number and this remainder. Okay, and then you check the same thing. Now you are finding out the HCF of B and A mod B. Then you ask, is B divisible by the smaller number A mod B? And notice that A mod B will be smaller than B, because if you are dividing something by B, you will get a remainder which is smaller than B. So now the smaller number is A mod B, and you check it the same way. If yes, then the smaller number A mod B is the HCF. If no, then you can do that. You can go on, proceed recursively, the same step. So simply like with numbers, it's very easy to see what he's saying, that if suppose you have to find HCF of 30 and 12, we did this before. So 30 and 12, you check, is 30 divisible by 12? No. So you will have to figure out HCF of 12 and 30 mod 12. And how much is 30 mod 12? That is 6. So is now you are figuring out the HCF of 12 and 6. So now you check if 12 is divisible by 6, and yes, so the HCF is 6. Simply speaking, you had to find out this HCF, then you figured out that this should be equal to this HCF, and then this should be equal to 6. But the important thing is, how did you figure out this thing? We will talk about that. We're just taking some examples to understand what Euclid said. Then we will figure out why this is true. So suppose the second example we had before was find the HCF of 1080 and 1079. Just take a look. First we are checking if 1079 can divide 1080. Of course no, the remainder is 1 now. So we have this thing as 1, and we check whether 1 divides 1079 or not, and then the answer is of course yes, and the HCF is 1. So Euclid have some insight into this, and he can calculate the HCF faster. So this is what happened, right? Okay. The key steps in the algorithm is when B divides A, then there is no problem. HCF of A and B is B. But when B doesn't divide A, then HCF of AB is HCF of B and A mod B. Why so? Let's go into it. Why so? So let's take an example. You have to find out the HCF of 30 and 12, and at some point in the algorithm you say that it is same as HCF of 12 and 6. Why do you say so? Right? So this is 12, right? 4, 8, 12. And this is 30, I think. 1, 2, 3, 4, 5, 6, 12, 18, 24, 30. Yes. So you have to find out the HCF of 12 and 30. So first you check, divide this 30 into 12. So what you get? What do you get when you divide It's like the obvious guess is like the biggest possible number which could divide both is could be that could be 12. So but when we divide 30 by 12, we see that there is one 12 in 30, then there is other 12 in 30, and there is a 6 remaining. This is 12, this is 12, and this is 6. So basically 30 can be written as 2 times 12 plus 6, or basically 12 plus 12 plus 6. So now you are figuring out the HCF of 12 and 12 plus 12 plus 6. You rewrite 30. 30 can be written as 12 plus 12 plus 6. And now you see, you checked for 12. It didn't turn out to be HCF because 12 will divide 12. But here, if you divide 12, so you will have 12 by 12 plus 12 by 12 plus 6 by 12. So this will be divisible, this will be divisible, but 6 by 12 is not a whole number, right? So there is the problem. The 6 is creating the problem, right? 6 is creating the problem. So you have 12 and you have 30, which is 12 plus 12 plus 6. So 12 is not the HCF. But anyways, whatever the HCF of 12 and this whole thing is, will also be the HCF of 12 and 6, because to divide 30 and 12, it's very important to divide 12 and 6. It's compulsory to divide 12 and 6. And then, for example, let's say 30 and 12 and 30 are divisible by 2, right? Are divisible by 2. So this is 6, this is 15. Because 2 can divide this 12, but 2 can also divide these 12s and this 6. So this 6 is very important. This remainder is very important. And that's why we understand that if we have to find out the HCF of 12 and 30, that should be the HCF of 12 and 6, because without, if you can't divide that 6, you can't divide that 30 if that number is dividing 12 already, right? So that's the argument. So HCF of 30 and 12 is the greatest number which divides 12 and 30. You can write 30 as 12 plus 12 plus 6. And by the logic which we discussed, HCF 3012 is the greatest number which divides 12 and 6. It's very important to divide the 6 here, the remaining 6 here. That's why HCF of 30 and 12 is HCF of 12 and 6, and then you know that the HCF is 6, right? Let's see how Euclid will calculate the HCF of 12 and 30. Let's not go into that. Yeah, let's think about more like in terms of pictures, we can also understand this thing. Suppose you have to find out the HCF of this red length and this green length. Suppose this length represents some number. So this red thing and this green thing. So you first of all you figure out whether this green thing, the smaller green line, will be able to divide the red line or not. So you see, you take another green line and say okay, this is more than 2 times the green line, and then you take another green line and you say that okay, this is the same. So the green length can divide the red length completely, and that's why the HCF is green length, right? This is the HCF, because this thing, the green, this is 1 times, like this length can divide both this length. This length can divide the green length 1 times and the red length 3 times, right? So this is our HCF. And sometimes you might not be that lucky, as we discussed. So suppose you have this, you have to find out the HCF of this green and this red line, right? And then you check whether the green line can divide the red line completely. So you have another green line and you check. So no, this is even less than twice of the green line. So what you have, there is a remainder. This yellow is the remainder there, and then you take this remainder, and now you forget about the red. this red thing here, you forget about that, and you concentrate and you apply the idea to this green and yellow. So now you're checking whether the yellow divides the green or not. So you take another yellow and it's divide, like 2 times this yellow length is green length. So that's why this is the HCF. If you don't believe, then you can check. This HCF will measure the red line in 3 times, and this same thing will measure the green line in 2 times, right? So this is the highest common factor of these two lengths. This is very interesting because from here you can go on talking about HCF of rational and irrational numbers also, because these lengths could be an irrational or rational number also. But just giving you a hint about this, because there was a student of mine who asked me about this thing, whether you can calculate the HCF of rational and irrational numbers also. And I said, the way I see it, you can only calculate the HCF for whole numbers. But then I was wrong at that time because I didn't see this happening. Anyways, thank you for watching. Have a nice day.